In this video, we are going to examine reactions of benzene. Typical reaction of benzene is an electrophilic aromatic substitution. Mechanism of electrophilic aromatic substitution involves reaction of benzene ring with an electrophile. So benzene is a nucleophile electron pair donor. Benzene donates a pi electron pair to form bond with an electrophile. This is a slow step and results in formation of the corresponding carbocation. The cation is cyclohexadienyl cation, and it is stabilized through electron delocalization or resonance. We can draw three resonance structures for cyclohexadienyl cation, and that's what makes it so stable. Note that positive charge is delocalized over the benzene ring or the intermediate cation, and positive charge is in ortho and para positions, or positions 2, 4, and 6 relative to the incoming electrophile. That will be important later in the next chapter. Now, typical reaction, such reaction of unsaturated systems with electrophiles, is followed by addition of a nucleophile to result in formation of an addition product. In this case, addition product does not form because addition product wouldn't have been aromatic. So such reaction would have been highly endothermic, and thermodynamically it would not be a favorable reaction. Instead, cyclohexadienyl cation loses a proton. So base, one of the bases present in reaction mixture, deprotonates cyclohexadienyl cation to restore aromatic ring of benzene. And the net overall result of reaction is replacement of one of the hydrogens on benzene ring with an electrophile. So the overall reaction is an electrophilic aromatic substitution. Electrophiles that participate in electrophilic aromatic substitution are what we call activated electrophiles. Benzene ring is a relatively poor electron donor. For that reason, ordinary electrophiles that we have encountered, for example, in addition reactions to alkenes, are not reactive enough. They are not electrophilic enough to react with benzene ring. Instead, we have to activate such electrophiles by complexing them, reacting them with either Lewis acids or Bronsted-Lowry acids. So we complex those electrophiles with some electron-deficient species to make them more reactive. And such more reactive electrophiles are suitable reagents for reaction with benzene. Here are some common electrophiles listed by class of reaction, and if you wish, you can pause video here and examine each one in more detail. We will now cover each one of those electrophiles in more detail in the order in which they are listed. First, we will examine halogenation reactions. Electrophilic aromatic halogenation is a suitable method to prepare chloro, bromo, or iodobenzene. Fluorine is not reactive as an electrophile, and fluorobenzene cannot be prepared by this method. Here we have examples of chlorination and bromination reactions. So, chlorine and bromine are activated by complexation with Lewis acids. Chlorine is activated by a reaction with aluminum trichloride to give chlorination reagent, and bromine with iron tribromide. To activate bromine, we of course could use aluminum tribromide or some other Lewis acid, but it's too expensive. Iron tribromide is much less expensive and much readily available. Also, in case of bromination, we can actually add iron itself in form of iron filings or even solid iron, like even a nail would work. And that would react with bromine to form iron tribromide. And since Lewis acid has to be added only in catalytic amount, only small amount is needed. So, for example, bromine with iron, if excess bromine is used, will accomplish the same reaction, because in situ in the reaction mixture iron tribromide will form and catalyze further reaction. Of course, we could use other Lewis acids for activation, and the outcome would be the same. The only limitation is that an ion of the Lewis acid has to match the electrophile. So we have used chlorides like aluminum chloride, zinc chloride, gallium chloride, So all those would work in chlorination reactions. While in case of bromination, we have used bromides like iron tribromide, boron tribromide, gallium tribromide, aluminum tribromide. Any of those would work. We cannot use different anions, anion different from nucleophile, because scrambling and exchange could occur and we could end up with a mixture of products. Here is how the activation works and how activated electrophile is generated. The actual electrophile, the actual electron deficient atom is one at the end of the molecule. So not one that carries formal positive charge, but one attached to it. So we have two chlorines. Chlorine with formal positive charge is attached to aluminum, but other chlorine atom is the actual electron deficient electrophile. And same goes for bromine. It's one that is attached to bromine with formal positive charge. Here is the reaction mechanism. So mechanism is simply a special case of general mechanism that we have seen already. So in this case, bromine is the electrophile, and you can see that pi electrons form a bond to terminal bromine, bromine at the end of the molecule. So carbon-bromine bond is formed that causes bromine-bromine bond to break. We have intermediate cyclohexadienyl cation, and then at the end a base, in this case iron tetrafluoroborate, removes proton from the intermediate cyclohexadienyl cation to give the product bromobenzene, and the resulting acid is actually unstable and decomposes to hydrogen bromide, which is reaction byproduct, and iron tribromide catalyst, which can go back to the first step, complex with another molecule of bromine, and catalyze another step. Of course, the same mechanism applies to chlorination reaction, just the electrophile is corresponding activated electrophile of chlorine. Halogenation reaction is carried out somewhat differently. Iodine is easily oxidized, and we use nitric acid as oxidizing agent. That oxidizing agent oxidizes iodine to iodonium ion. And this way, actually both atoms of iodine, from molecule of iodine, could be used. And in a reaction, of course, we get better use of iodine, and that's the method to prepare iodobenzene. So we mix iodine and benzene and add nitric acid, and product is iodobenzene. Note that in previous two reactions, chlorination and bromination, one atom of chlorine and one atom of bromine was wasted as a byproduct, as molecule of HCl or HBr. So only 50% of chlorine or bromine could be incorporated into the final product, halobenzene, while in case of iodine, we can, in theory, have 100% yield with respect to halogen. In an electrophilic aromatic nitration, the activated electrophile is nitration mixture, and that's a mixture of nitric and sulfuric acids. So reaction of benzene with such mixture results in formation of nitrobenzene as reaction product. Byproduct is molecule of water. Here is how mixing nitric acid with sulfuric acid activates the electrophile, provides activated electrophile for nitration. Sulfuric acid is stronger than nitric and protonates nitric acid. Protonated nitric acid loses molecule of water to give nitronium ion, and this nitronium ion is electron deficient, so this is the activated electrophile. Now nitronium ion as an electrophile reacts with benzene to give intermediate cyclohexadienyl cation. We have already seen that before. And then one of the bases present in reaction mixture, for example, molecule of water, deprotonates cyclohexadienyl cation to give the final product, nitrobenzene. Electrophilic aromatic sulfonation utilizes fuming sulfuric acid as the activated electrophile. Fuming sulfuric acid is solution of sulfur trioxide in sulfuric acid. Sulfur trioxide itself is plausible reagent because it's pretty strong electrophile and may be capable of reacting with benzene ring. When it's dissolved in sulfuric acid, it is protonated, and then even stronger, even better electrophile is generated. There are two proposed mechanisms for this reaction. First mechanism, that's earlier mechanism, involves donation of electron pair, pi electron pair from benzene to sulfur trioxide to generate the intermediate cyclohexadienyl cation. And now in an intramolecular reaction, so intramolecular within the same molecule, there is proton transfer from carbon to oxygen. This proton transfer accomplishes two things. It restores aromatic ring and protonates oxygen, so the final product is obtained. Final product is benzene sulfonic acid. This mechanism is unlikely because it involves cyclic transition state, four-membered cyclic transition state. It is unlikely because electron pair from oxygen has to be donated to hydrogen opposite from carbon-hydrogen bond that is being broken. And that's obviously not possible if transition state is cyclic, it is four-membered ring. Then electron pair from oxygen cannot come from the backside. So we have alternative mechanism where stronger electrophile protonated sulfur trioxide is involved, and intermediate cyclohexadienyl cation loses proton to an outside base. So the proton removal is an intermolecular process. And then, of course, as before, benzene sulfonic acid is generated as the final product. Unlike most electrophilic aromatic substitutions, electrophilic aromatic sulfonation is a reversible reaction. So it's somewhat unique in that respect. So when benzene sulfonic acid is dissolved in dilute aqueous acid and that solution is heated, benzene sulfonic acid loses sulfur trioxide and benzene itself is obtained. So this is reversible reaction. So as you can see in the bottom equation, we can treat benzene with fumic sulfuric acid to obtain benzene sulfonic acid, and we can reverse that process by treatment of benzene sulfonic acid with dilute acid and heating it. That's convenient sometimes if we want to block particular position on benzene ring. We can then introduce sulfonic acid group and then remove it. In a Friedel-Crafts alkylation, alkyl chloride is activated by aluminum chloride to give activated electrophile. Products are corresponding alkylated benzenes. Structure of the activated electrophile depends on the nature of the R group, of the alkyl group. If alkyl group is primary, then carbon-chlorine bond is covalent bond. It's polar covalent bond, and carbon is the electron deficient atom. We can see in this formula that it's chlorine attached to aluminum that carries a formal positive charge, but actually carbon attached to that chlorine is the electron deficient atom. If alkyl group is secondary or tertiary, or is primary that could rearrange to secondary or tertiary, then the activated electrophile is ionic compound. It is actually carbocation and it's accompanied by corresponding anion, aluminum tetrachloride anion. Reaction mechanism involves, of course, reaction of the electrophile with benzene ring to give the intermediate cyclohexadienyl cation, which then loses proton, and product is corresponding alkylbenzene. As in case of chlorination, the byproduct is the same, and so the resulting acid is unstable, decomposes to hypochloric acid and aluminum trichloride, and aluminum trichloride then can serve as a catalyst in the next reaction, can complex with another molecule of alkyl chloride and catalyze another reaction. So this means that Friedel-Crafts alkylation is catalytic with respect to the Lewis acid. Friedel-Crafts alkylation in general actually is not the best method to prepare alkylbenzenes. There are several problems with this reaction, although in certain instances it can work very well to give particular product. Those instances are relatively rare. There are two main problems with Friedel-Crafts reaction. First is that it involves rearrangements, and even primary substrates will rearrange in the course of preparation of the activated electrophile. If primary group is anything larger than ethyl group, it will rearrange to secondary cation. So as you can see here, 1-chlorobutane reacts with aluminum trichloride to give secondary cation, so 2-butyl cation. And then reaction with benzene ring actually results in formation of mixture of products, because rearrangement is not complete, not all of the starting alkyl halide rearranges, so we get mixture of products. And that, of course, that means that desired product is never obtained in good yield, and in addition, since these products have very similar properties, they are actually very difficult to separate from each other. So this is first problem, rearrangement of the alkyl group to give mixture of products. Second problem with Friedel-Crafts alkylation is that Alkylbenzenes are more reactive than benzene. Since Alkylbenzenes are reaction products, then that means that as soon as some alkylbenzene is formed, it's likely to react preferentially in Friedel-Crafts reaction preferentially to benzene. So product will likely get alkylated again rather than some of the benzene that was not alkylated yet. And so the products will be then dialkylbenzenes, and then dialkylbenzenes are even more reactive, so they get alkylated again, and we end up with trialkylated benzene, then tetraalkylbenzene, and eventually reaction stops, further alkylation stops because of the steric hindrance. But nonetheless, we end up with complex mixtures of di, tri, and tetraalkylated products. First of all, desired product will always then be formed in poor yield, because there will be so many other byproducts, and secondly, they are of course very difficult to separate from each other. Even though there are numerous problems with Friedel-Crafts alkylation, still this reaction is useful for certain purposes, and it's actually a common industrial reaction. And in industry, frequently other substrates that can generate carbocations are used in Friedel-Crafts alkylation. Of course, any species that can generate carbocation could serve as alkyl electrophile and is suitable substrate for Friedel-Crafts alkylation. So, for example, alcohols upon treatment with sulfuric acid lose molecule of water to generate intermediate carbocation, so that's one possible activated electrophile. Another method particularly commonly used in industry is activation of alkenes with hydrofluoric acid. So addition of hydrogen fluoride to an alkene results in formation of intermediate carbocation and then subsequent Friedel-Crafts alkylation. Or alternatively, we can use Lewis acid for this purpose. A Friedel-Crafts acylation involves placing of acyl group on benzene ring. So acyl group is a keto group, and we end up with various phenols as reaction products. Activated electrophile is prepared in a reaction of acyl chloride, so chloride of carboxylic acid, with aluminum trichloride. And the activated electrophile is acylium cation. Acylium cation is very stable cation because it's stabilized through resonance, through electron delocalization. It's stable cation and very strong electrophile. So ideal substrate for an electrophilic aromatic substitution. Also, because it's such a stable cation, there are no rearrangements. So this is much better method for electrophilic aromatic substitution compared to Friedel-Crafts alkylation, because acylation does not involve rearrangements. In addition, placing acyl group on benzene ring means that one is placing deactivating group on benzene ring. So product is less reactive compared to starting benzene, which means that there are no problems with multiple reactions, with polyacylation. Only single acylation occurs and then reaction stops there. Reaction mechanism involves electron donation of a pi electron pair to acylium, from benzene to acylium cation, and formation of the intermediate cyclohexadienyl cation. Loss of proton results in a formation of corresponding phenol or acylbenzene. Now it is interesting that unlike other electrophilic aromatic substitutions that we have encountered so far, this one is not catalytic. Actually, looking at the mechanism, it should be catalytic. but it is not catalytic because resulting product is a nucleophile, a Lewis base, and will combine with Lewis acid catalyst and form a complex. And so once product is formed, it takes what should be catalyst out of the reaction. It complexes with it and basically stays there in form of a complex. So for that reason, we have to use stoichiometric amount of Lewis acid. And then after reaction is completed, we have to add additional workup step and decompose this complex by addition of water. So reaction is not catalytic, not because reagent requires stoichiometric amount of Lewis acid, but because the product complexes with Lewis acid and takes it out of the reaction. As already mentioned, alkylation of benzene by Friedel-Crafts alkylation is not a very good method to cleanly and selectively prepare monoalkylated benzene. Problem is that reaction occurs with rearrangement, and there are often polyalkylations. That's shown as an example here in an attempted alkylation of benzene with 1-chlorobutane in presence of aluminum trichloride to produce butylbenzene. There are numerous byproducts, and the desired product would be obtained in very poor yield. But at the same time, Friedel-Crafts acylation is a very good method. There are no rearrangements, and there is only monoacylation. The only problem that product is acylbenzene, not alkylbenzene. We can exploit still acylation to prepare alkylbenzenes if we follow acylation step by a reduction of acyl group to alkyl group. And so here is how we do it. We treat benzene, in this case if we want to prepare butylbenzene, we treat benzene with butanoic chloride in the presence of aluminum trichloride, followed by aqueous workup, and that gives a corresponding acylated product, in this case butyraphenone. Then we can reduce that. Reduction can be carried out, for example, as Clemmensen reduction using zinc or tin, for example, some active metal. Often it's an amalgam, although we can avoid use of mercury. Amalgam is there only to moderate reactivity of zinc. So zinc and hydrochloric acid, with or without heat, it may work without heat. Or we can carry out reaction as Wolff-Kirchner reduction. That's reaction in a sealed tube with hydrazine and potassium hydroxide at very high temperature. Either way, carbonyl group is reduced to methylene group, CH2. And in this case, we would obtain butylbenzene cleanly and in high yield. Second example is even better example, where we have cyclopropyl carboxyl chloride as reagent, and you can see there are no rearrangements, no opening of cyclopropyl ring, so reaction works very well, and desired product is obtained in excellent yield and high purity. So Friedel-Crafts acylation reduction sequence is favorable method to simple Friedel-Crafts alkylation to prepare corresponding alkylbenzenes. This completes our study of reactions of benzene. Next, we are going to look at reactions of substituted benzenes.